Okay, our next speaker we have is Maxime Ripard from Red Hat, giving us a talk on functional safety. So welcome, Maxime.
Thank you. So, hi everyone. So, just like Kevin said, I'm Maxime Ripard. I'm working for Red Hat as a software engineer. And I've been working on automotive functional safety for the last couple of years. And so I've been discussing the talk with a couple of people in the morning when we joined, and they were all saying, oh, is it the ASIL something thing? And I was like, yep. So hopefully you will get an idea of what the ASIL something is at the end of the talk and what we've been working on. And so my background is definitely on the kernel side of things. I've been an ARM platform maintainer for close to 10 years, up until a couple of years ago as well. And I'm part of the DRM maintenance team, so it was something that was very new to me, but also something that I was kind of afraid of, I guess. You know, involving a lot of constraint, paperwork, and it just cannot work. Hopefully, I will also address those questions during that talk. So, as far as cars go, as you have probably noticed, there's been more and more software components in them. If you use some that have been produced in the last, I don't know, 10, 20 years. So I was born in the 80s, and the car in the 80s looked like that one. It was pretty simple. You didn't have any anti-blocking system for the brakes. You didn't have any kind of active suspension, stability assistance. It was a very simple thermal engine that didn't have any kind of injection, no airbags, no ADAS, no in-vehicle infotainment. It was basically a radio and cassette player if you were lucky. And so they basically didn't have any software in them. If we're looking at a car right now, so if I Googled for a modern car, this is what I got. I don't own a car, so maybe it's not what it actually is, but allegedly a modern car is like that. So it's either an hybrid or an EV. You do have driving assistance systems like lane keeping, ESP, adaptive cruise control, park assist, autonomous driving for some of them. You had plenty of airbags, emergency braking. You have a nice infotainment platform that can run Doom and other things as well, I'm sure. And so software is basically everywhere and is one of the major selling points. And I think that's one of the main difference between even cars that were produced in the 90s that started to have some software. That software started as a way to improve the mechanical point of view of the car, but slowly it gained more and more traction, and now people are expecting software to be capable. We were taking a rental on Monday, and the driver was complaining that the GPS maps were not up to date, for example. And sure, that's frustrating, but it's also part of the software, and so we expect the software to keep up and be at least on par with what we get on our phones every day. The thing is, when you're running software on a car, some parts of the car are kind of critical, and some are not. So on the life critical side of things, you have the automotive driving assistance, you have the braking, airbags, basically the things that can either stop you if you have an issue or protect you if you have an accident. Some are just here for comfort, like, I don't know, AC, radio, infotainment, whatever. And so it used to be mitigated by the fact that we had different hardware platforms in the car that were running those different criticality levels. So we had a computer dedicated to infotainment that didn't have any kind of criticality issue. We have a computer dedicated to braking. We had a computer dedicated to, I don't know, lights, for example, in general. But the industry has moved from having those multiple computers in the system to having central ones, or a central one. And it was due to several factors. The first one has been the chip shortages during the COVID epidemic, where it was very difficult for software companies, for car maker companies, to source those chips in the first place. So sourcing one is always easier than sourcing 4, let's say. We do expect, as user, to have an up-to-date platform with up-to-date software, and so it's always easier to update a single computer than to update dozens of them in a system. And also, it costs less to have a single chip in the car than 4, so it's nice for the shareholders as well. And so that single computer in the system will have to handle and manage different applications with different criticality level, and that's what's called mixed criticality. And so mixed criticality is one of the things that is being defined by basically the major standard for automotive safety, which is ISO 26262, which is called functional safety for road vehicles. And so as far as safety goes, so it's still fairly new. So it was first ratified in 2011 and got certified. There was a new revision on 2018, and it applies to basically all road vehicles but mopeds. So yeah, all road vehicles. And so it considers only functional safety, and you have 2 other aspects of safety in a car, which are active and passive safeties. The passive safety is basically things like crumpling zones and whatever. It's passive system in the car that will protect you. And active safety is the active system in the car that will protect you as well. So airbags, for example, are active safety systems. Seat belts are passive safety systems. And so functional safety is only about electronics. So functional safety can still affect, let's say, airbags. And so it's a combination, like having a safe airbag is a combination of both active and functional safeties, because functional safety will just make sure that the software can react to the event of a crash, for example, properly and trigger the airbag. The active safety of it will make sure that it deploys in enough time for you not to just crash onto the wheel if you actually have a crash, that it's big enough to hold your weight, whatever. So it's more of the mechanical side of thing, and functional safety deals with the functional part of it. And so the main topic being discussed in the ISO 26262 is risk levels, and those are what ASIL, that I was talking about before, are about. And so it's basically a classification based on what if a defect happens, what will be the consequences of it, what is the probability of a driver or a passenger mitigating it, and the probability of someone being injured during that event. So it has 3 main criteria. The first one being severity, which is basically whether you will walk away from that defect, from the consequences of that defect, with just scratches or you will be dead. Exposure, which is basically the frequency of an injury happening. So, for example, you could have a very serious defect, but if you're never going to be injured, it's less important that if you're always going to be injured. And then controllability is about whether it's something a driver or passenger can recover from. And so it goes from something that it's totally controllable and the driver can definitely mitigate the issue, or something that is basically uncontrollable and you can't do anything about it. And so the classification starts with ASIL D, which is fatal, high probability of injury, and uncontrollable. So basically you're fucked. And if you reduce any criteria by 1 level, you reduce the ASIL level by 1 level as well. So if, for example, you had the same probability of injury and same controllability, but the injury was, for example, you would get scratches, then it's 3 levels down, so it will be level ASIL A. And so it goes back to ASIL A, and something below than ASIL A is called quality managed, which is just a nice term for basically we don't trust this. Like this can be anything. We just got it from some random website and it runs on our platform. So QM means that any risk associated with the hardware design is manageable, and so we can do whatever with it, use any language, any software development practice, you know, whatever. And so examples of defects that could be classified at various ASIL levels would be, for example, ASIL D is a total loss of braking. So we go back to it's fatal, uncontrollable, and high probability of injury. But for example, if you have the loss of rear braking, then it's something that you probably can control somehow. The probability of injury is also lessened a bit. So yeah, headlights being gone is also something you can quite manage as a driver in some circumstances. For example, if it's day, then you don't care about it. But also, most of the time, if it's during nighttime, then you can probably just stop too. ASIL A is things like daylights, and QM is, you know, the radio app or the weather app on your IVI system. And so in the spec, the real heavy ones are ASIL C and D, which recommends things like having formal methods, require verification of design of the binary as well. They highly recommend using subsets of languages to, for example, for C, that remove the dangerous part of the C language as well. And so it's something that really has to be designed, that the software has to be designed for ASIL C and D. We were talking with someone earlier as well, which was describing that they worked on an ASIL D before, and they had to make a periodic check of basically the CPU still being able to execute instructions in the expected state. So they basically were running all instructions in the CPU every 2 seconds and making sure that the state was what they were expecting. So it's like very handed, but anything below that is actually much more manageable. It doesn't require formal methods anymore. It doesn't really encourage you to use language subsets. So it's something we could use and certify quite with a quite reasonable effort. Another item that the spec, the ISO certification is describing is something that is called freedom from interference, and it's basically the main thing. And it's described as the absence of cascading failure between components that could lead to the violation of safety requirements. Basically, it means that an application must not affect another. And especially an application that is, for example, QM must not affect a ASIL something application, no matter what it does, no matter if it goes rogue, if it crashes, like whatever happens to that application, it must not affect the others. And so there's several things that are described in this as an interference. There's the spatial interference, which is basically an application cannot just access another application memory or corrupt it. The temporal interference, which is the application must not be able to deplete another application of CPU execution time, basically. And then you have the resource interference, which is basically it must not interfere with any shared resource between applications. So it would be like clocks, file in the file systems, power regulators, power budgets, any kind of resource that is actually shared, both logical and hardware. And when you think about it that way, then it's basically just OS design. Spatial interference is what we have processes and we are using the MMUs for. Temporal interference is why we have a scheduler for, and resource interference is why we have frameworks that are able to neutralize resource access and permissions in file systems and so on. So it's actually what we've been doing all along, right? We were doing automotive safety and we just didn't know it. And so in order to achieve these goals, we had multiple architectures that have been suggested and developed over the years. And we had, so as we were discussing before, we had the first one that was basically just separating the various computers by criticality and going along with it. Then we had also things like heterogeneous systems where we could have multiple systems running on several cores in the system, split by cluster or whatever, or an RTOS running on the microcontroller while Linux is running on the main CPU or things like that. Then we had VMs, but we could also argue that, for example, containers kind of fall into that isolation, or process sandboxing could as well. And so if we're looking at it, the first design we had was different hardware with different ASIL level. Then we had one single piece of hardware, a certified hypervisor, and then different VM, each VM running a different level of criticality. And this is basically where we are at right now with Linux. Every time you're, so when you're reading something about automotive Linux, for example, Electrobits and Ubuntu had a partnership that was released a couple of months ago. Actually, what Ubuntu did is making a QM VM with Ubuntu, so basically a distribution for the VM, QM VM running on top of the certified Electrobits hypervisor. QNX has something that is quite similar. But we could also just do it with Linux, like no VM, no multiple computers, just, just a single OS. To deal with the temporal interference, we could use the scheduler, preempt RT, C groups to allocate time slice in the scheduler for it as well. For spatial interference, we could have, we could basically rely on the process address space, and again, C groups, containers, namespaces, whatever, things we are quite used to now. For resource interference, we can do QoS, arbitration between the, multiple processes, accessing the same devices, partitioning where it makes sense as well, and all the other issues that we typically have with embedded systems, like how to do an update reliably, how to do secure boot, how to have a fast boot time, how to have a flicker-free boot for the display, everything we kind of talked about today. And so it would look something like this. So you get a single computer, and then on top of that, you basically just have Podman, possibly systemd computers, and then different systemd slices, namespaces, C groups, whatever, running different kind of workloads and criticality depending on those. And so in this case, the automatic braking system, for example, would be running just as a container in your platform. Any safety application would be running as Podman or systemd slice or whatever, and then you could also have just a QM container running whatever. That's just like the easy part, right? We know we have a system that is robust enough, but how do we actually make it ISO 26262 compliant? And so just like most certifications, it's usually done by a certification authority. And so you need to prove to that certification authority that your design is indeed robust enough for what you claim it is, but also that you didn't really miss anything, that it has been reviewed, tested, documented, that you will keep doing so as well. And so you have processes in place that if it is tested, then show me that the tests are actually running. And so you have to prove all of that to a certification authority. It's quite a large document. It requires quite a lot of software effort as well to ramp up the tests coverage. It's also something you need to prove, right? If you claim that you test your product enough, you have to provide a definition of what testing that system enough is and why you think it's enough. So for example, if you want to have a 70% test coverage, then fine, but why 70 and not 60 or 80? And so when you go through all that paperwork, at the end of the day, or year or years, you would get a certification attestation that is only valid for a given version. So every time you're doing an update, then you need to restart that whole certification process. But again, if from one version to the other, if the certification authority was fine with version A, if the only thing you made is an upgrade to the kernel and the libc, let's say, then it's probably going to be easy to prove that version A+1 is still safe because you didn't really change anything to your design or test suite, whatever. So it will be much simpler for the next version. So it works fine, but we're still missing a lot of things, especially in the graphics space, but not only. We were discussing it at the Media Summit, but for example, one sticking point is that you get plenty of IOCTL, especially in v4L2 and DRM, that allows you to allocate a buffer from the user space, but are not tracked anywhere. So you could very well have an application that starts allocating buffers from those IOCTL, and you can't enforce any limit, which breaks FFI. Similarly, you can't really control or limit the scheduling policies of a GPU. There's some work happening for it, but it's not done yet, so you're breaking FFI again. But this time, so the first one was spatial interference, second one is temporal interference. The clock framework has an issue as well, which can lead to a major clock, basically a lot of clocks changing rates, including the one that haven't been notified, which breaks resource interference. And then you have completely missing features because we just didn't really care about automotive safety so far, at least upstream. Like OpenGL and Vulkan both have specific APIs for safety certification, safety certified, workloads, which are called OpenGL and Vulkan SC, which are completely missing from Mesa. v4L2 has kind of a nice feature, let's say, that if a sensor is removed, you don't have any camera present in the system at all. So if your system had multiple sensors, like a car, and you're missing one because your side mirror got broken, then you don't have any camera accessible anymore. So we need to work on that. There's a nice thing as well. In the certification, you need to, the telltale signs in your dashboard, which say when your engine has a defect, when you're running out of oil, water gets too high, whatever, it actually needs to run even if the compositor has crashed. So we need to be able to find a system that allows to have an application that can draw on a limited part of the display without the compositor involvement, and also being robust enough that if it crashes, it won't corrupt the screen that the application is displaying on. And then we also need plenty of virtualization features so that if we want to run VMs, we have access to usual embedded devices that aren't really covered by any VM at the moment, like, I don't know, codecs. GPUs are kind of weird as well because you expect pass-through, but pass-through doesn't really work there. So yeah, plenty of work on the virtualization side of things as well. So hopefully we'll work on all of them. Work has started on some of them, but we should complete all of them. Yeah. Any questions?
You said we are working on them. Who's we?
So there's multiple people interested. AGL has been here for a long time, and AGL, I believe, hasn't really worked on the kernel side of things because it's mostly about it's an upstream community that works on different projects that are related to automotive grade Linux, but it's not a consistent product, it's not a distribution, and so it's basically just a place to put efforts into. So they haven't really worked on the kernel as far as I know. But in my case, we is Red Hat, because we've been working on that OS for some years before I even joined. So we started that work with the help of other people, obviously.
Just a comment. I don't think they're working on ASIL stuff, but I know Elisa is working on a lot of, Elisa is the, what is it, enabling Linux and safety applications or something like that. Linux Foundation Group is working on a lot of aerospace stuff at the moment, and medical, I think. And so I think there are different, is ASIL automotive specific spec, or does that cover functional safety in other domains?
So ASIL is automotive specific, but it's an implementation of a wider spec, that applies to any industry. And so you usually get dedicated norms and standards applying that wider spec to specific industries. So ASIL is automotive specific, but yeah, you have similar standards in other like spatial airplanes and other industries, yeah.
Yeah, thanks for this talk. In industry, it's EAC 61508 norm. Question, so on your side, do you have a specific hack you are pushing to have this certified with TUV? I guess it's with TUV, I guess?
No, it's with Exida.
Okay. So do you have any specific stuff we need to add, or is it everything available? Or I'm not sure to have well understood that part.
So we've worked on an MVP so far. So we are working on a minimal product at the moment. So like that's why I was telling you that graphics are not available yet.
Yes.
It's because like it's not ready yet as well. But so for the minimal part we have, it's the OS we've been working on, which is called Red Hat In-Vehicle OS, which is kind of a mouthful, but is based on Rail. So at the kernel level, at least, it's kind of a derivative of Rail. So we do have some kernel patches compared to upstream, but it's mostly backports, and yeah, the usual Rail stuff.
And just one more. On what you were showing us with the example with a Podman for the braking system, so like this you can reach ASIL B.
Yeah.
But for this, so I guess you have another, you have something else to complete to reach ASIL D for the braking part?
We're not trying for ASIL D.
Okay.
It would be like, and usually it's, so for example, for brakes and whatever, it's MCUs directly on the braking system. It's still separate controllers because it's so specific and so hard to get certified and requires so much stuff that like it's much easier if you're doing something simple and just dedicated to that purpose. Okay. So we are trying for ASIL D, yeah. Okay. B, sorry.
B.
So in this picture, where you have both an ASIL B application and you have a ASIL B container, what about the lower levels? So is Podman and Systemd and the Linux kernel, are they also ASIL B?
Yeah.
Okay.
They would be certified as well. And so we've started for some time, we've gradually certified. We haven't certified the thing as one thing, and so we've continued certification, but the one thing that has been certified by an authority yet is precisely the way we're dealing with mixed criticality. So that part is already approved, essentially, and ASIL B certified.
But Podman and Linux kernel are quite large pieces of code, so how much effort is it to take in a new version of, for example, the Linux kernel?
It's what I was kind of hinting at the end, right? If you have a Linux version already certified, then it's pretty easy to certify a new one because you already have all the test suites, all the documentation, you just have to update it, essentially. You don't have to create the whole thing. So it's some work, but it's far less work than like reaching the initial milestone.
How are you managing the, let's say, great part of the kernel you're probably not using? So you are, I assume you are focusing on a very specific and limited scope inside the kernel at least?
Yeah. So we have several ways to manage it. So there's, in the documents we produce, we have several things. The main ones being relevant at the moment are things that are called assumption of use and recommendation of use. And so it's a way for us to say, for example, that we consider a part of the kernel or the system to not be safe or not safe if you start using that particular features or whatever. So I don't know, let's take signals. Signals are kind of notorious for being hard to handle properly and can be dispatched to the wrong thread, whatever. So one way we could solve this is basically say, well, just don't use signals if you want to be ASIL B certified and use signal FD instead, for example. So that's one way. The other way is just disabling stuff in the kernel. So like I was saying, graphics aren't there yet, then we just disable the whole graphics support in the kernel, and so that helps too. And then there's a couple of things that are also something we defer to other entities. So for example, source of defects can be the firmware having a bug, for example, or the device tree being wrong, or things like that. And in this case, we would create another assumption of use that we assume the firmware behaves properly. We assume the device tree has been written down properly, and so we know that, because if we don't, then there's no way the system can be safe. And so the firmware would have been certified anyway, and so it's only the combination of a certified firmware and a certified OS that make the whole thing work together, and certified hardware as well. But otherwise, yeah.
Another question, disclaimer, I work for an automotive company, and for us it's really, really far, this part. But how are you coping with, for example, the MISRA C requirement, let's say? So you're
The what, sorry?
The MISRA rules, for example, or coding rules that probably is not really strictly enforced by the 26 tool.
Yeah, I don't know about that, sorry.
Okay.
What about the hardware? Does it also need ASIL B certification, and is it available?
Yeah, there's some hardware, like especially in the automotive space, like TI has automotive SoCs, Renes, well, I'm sure you know Renes has some too, and the hardware is certified, and they provide certified firmwares as well.
So for this automatic braking system, do you need to guarantee a specific latency so you are an ASIL B? Because I am wondering about like cross interference because of caching, for example. Then you get you need to load more stuff into the caches. You need to take more time.
Yeah. That's a good question. I haven't really worked on that part, but since we are claiming that it's free from interference, then if we are certified, then we are safe on that front, I guess. But yeah, so yeah, for caches, I'm not sure how it works.
So there are processors that have support for pinning stuff, but
Yeah.
I'm not sure if Linux can handle that.
Yeah, I don't know there, sorry.
Yeah, there is some cache partitioning for that. But it's not all processor, but certified processor, I guess, you can use that, yes. And Linux supports since kernel, don't remember which number.
So I see in the SLB Telltales, you added it as a traditional application. So for Telltales, you will need basically a safe display or display in a safety context. So in this case, since you are driving Telltales, so if there is a failure in the display, like a freeze frame or something, right? So you need to do some correction, notify the server that is controlling the display, right? Now there is no API in the KMS to support this freeze frame detection, or there is no error recovery path also defined. And to support an API, we need any display server to have a use case for it. So what display server you will account for, right? Because unless display server supports an API, we cannot add support in the driver or the DRM also. So it's a chicken egg problem.
Yeah, for the Telltales issue, indeed, like we probably need some hardware assistance and also a lot of work on the KMS API and Wayland interfaces as well, probably. Yeah.
And does the spec define some recovery mechanism, like let's say camera failure is there, then we just catch the error interrupt, or we should reset the pipeline, or we should, if there's a display failure, we should have some tolerance, let's say of 100 frames, or until 100 frames are continuously, have the same checksum, then only we reset the display. So does the spec define, or we can define it ourselves, or user defines it on what should be the tolerance to recover or reset the pipeline?
That's a good question, I guess. I don't really know. We haven't really figured it out yet either. So, like, maybe I'll come back in a couple of years and let you know about it.
Yeah, because we had this support in the hardware for all these features, but
Yeah.
API doesn't support it, and we are told that since the display server doesn't support it, Western doesn't support it, so we cannot add it. So it's a bit difficult, like, because Western we cannot add freeze frame detection because it's mostly used on the desktop. So
Yeah. But also, we have been discussing whether we can rely on the hardware supporting it. So we know some platforms, like from TIs, for example, have dedicated hardware and mechanism to talk with the firmware and so on to help there. But is it enough? Should we also be able to do it purely in software? It's one of the things we've been discussing, and we're not quite sure yet.
okay, thank you.
So could you go back to the slide where you show the current situation about the partitioning?
Which
Yeah.
one?
Well, any of the two. While I understand the push to reduce the number of hardware components, for whatever that is safety critical, what is the advantage of going for a solution which doesn't compartmentalize the hardware with a hypervisor compared to running anything natively? So everything that is ASIL B, which is like a braking system, wouldn't be safer. It's compartmentalized with an hypervisor instead of running inside a complex system like Linux system is.
It wouldn't be less safe. I'm not sure if it would be safer the other way around, but like running on a single system, the argument is that it's not less safe. And so it allows you to still, I mean, at the end of the day, it's also a trade-off with other things, right? Whether how many software licenses you want to pay for, how many, what kind of development ecosystem you want to use as well. And it's one of the strong advantages for Linux as well. And it's why we've talked about Linux and embedded like 15 years ago. It was why it was so much convenient to use on embedded systems, because we had all these things already available. Then here it's kind of the same argument, right? Writing an ASIL application in Linux is just much better because you have access to all the open source libraries, you have access as long as they're certified. But open source compilers as well. So there's still some benefits to it that are not strictly related to safety. And so if we're deemed ASIL B compliant, it means that we are not less safe, we're just as safe. So yeah, it's good enough, basically.
Can you, on the one more slide, the big stack with the containers, so
Yeah.
can you say a little bit about what the proprietary competition is today in this? I know about QNX, but what are the other big players in the proprietary space?
They all have the VM-based architecture, and so yeah, they all have their own certified hypervisor. Basically, there's no, as far as I know, there's no competition with that architecture. So yeah, there's QNX, which have their own hypervisor. Electrobits is one. And yeah, those are the two main ones, I think, or the two I can think of at least.
One last question?
Could you provide any information about the kind of testing that you are running to obtain a certification, or a general idea about what kind of testing?
I mean, it's the usual testing we are used to. I mean, it's mostly integration testing, I guess, but yeah, unit testing, like the usual test suites we are used to.
So you're not testing against like this particular process should perform in certain thresholds of timings or other very specific?
We do test for latency, for example.
Okay.
Yeah.
Okay, thanks.
Yeah, sorry, it's one of the things I was thinking about when I mentioned integration testing. Yeah.
So preempt RT is enabled in that kernel. Yeah. Okay. Okay. Thank you.